Thank you. Thanks everybody. I would like to thank the organizers for inviting me to this really inspiring conference. I also want to apologize. Maybe there are a couple of people in the audience that heard me speak about this. Maybe I'll give a slightly different twist on this talk. But so I'm not going to say anything arithmetic, since I don't have anything arithmetic to say. But I'll try to address one aspect that has been present this week in many talks, which is this understanding that in this way of trying to understand functional theoretic invariance, in number theory, functional theoretic invariance like L functions as coming from geometric structures on character varieties of moduli of Gauss representations. There is always some interesting and non-trivial straightening rectification process that's needed that starts with the geometric structures and converts it into a function. And so I want to address that aspect of the problem in some generality. And so that's what I'm going to talk about in a slightly more general in a different context, but hopefully it will be applicable to the arithmetic setting eventually if somebody puts their mind to it. Okay, so this is based on some sequence of joint works, some of them written, some of them not, with many people, Kalaka, Tsarkov, Toan, Vesosi, and Vaki. And so I'm going to do a very quick excursion in derived symplectic geometry and shifted symplectic geometry, because this is the type of geometric structure that gives rise to those functions. And then I'm going to try and set up the problem of actually understanding when are these structures coming from functions, and that has something to do with actually the existence of foliations. So I'm going to talk about foliations in derived geometry briefly, and then talk about these derived Darboux theorems, which are the theorems that produce the functions, and we'll then show you some hopefully interesting examples. Okay, so very quickly, I'm not going to delve into the shifted symplectic geometry, but let me just point out the highlight. So if you have a smooth space, say over the complex numbers, symplectic structure, it's a closed algebraic two-form, such that the contraction with that form on vector fields gives you a map to one forms, and that map is a Schiff isomorphism. So that's the non-degeneracy condition. And then there is an integrability condition, which I put into saying that the form is closed. And if you try and generalize this notion, this concept to more intricate geometries, it doesn't quite work. So if X is singular, or if it has some fuzzy structure that's coming from its intrinsic geometric nature, say it has some stackiness with automorphisms at each point, or it has some nilpotence or homological nilpotence in its function theory, then taking, then your infinitesimal data is much more complicated. So taking derivations of the algebra functions or taking scalar differentials is not, these are too crude invariants. You need to replace them with the tangent complex and the cotangent complex. So you already in that setting, when you have these decorations in the geometry, or when you have singularities, you have to work with homological notions like the vector fields and the forms become complex and become changing complexes or co-changing complexes. And an artifact of that, so in particular, your notion of non-degeneracy, which was the notion of saying that two shifts are isomorphic, will now become a homological notion. It will say that two complexes are quasi-isomorphic. Okay, so that's not a very big price to pay, but there is another subtlety, which is that the moment you have this internal homological degree, the notion of being closed gets modified by the differentials in these complexes, and it becomes actually an additional structure rather than just a condition. And so I'm not going to go into that. If you can ask me afterwards if this is the first time you see this stuff. But let me introduce the basic notion. So if you have a derived space or a derived Artin stack, which is in this world of derived geometry, it behaves like a smooth guy. So it's what we call locally finite presentation. So that means in practical terms that the cotangent complex or the tangent complex are actually perfect complexes. So if you have one of those guys, then you can talk about two forms. So these are maps from the structure shift to the second wedge power of the cotangent complex. But because now we're dealing with complexes, it's useful and in fact necessary to introduce an additional homological flexibility. So I'm going to talk about shifted two forms. So this will be mapped from the structure shift to the second wedge power of the cotangent complex, shifted by some integer n. And so such a two form, well, up to isomorphism, it's in H0 of that complex of maps. It's non-degenerate if it's a contraction with it, gives you a map from the tangent complex to the n-shifted cotangent complex, and you would like this to be a quasi-isomorphism. So that's the non-degeneracy condition. And then, as I said, there is some meaningful intrinsic way of saying what integrability on those guys is. So the space of n-shifted forms has a refinement to a space of n-shifted closed two forms. And that requires putting in extra data. So the closed forms are guys which are closed with where the closing condition is taking into account corrections that are allowed by putting images of the internal differential in the cotangent complex. So the DeRam complex generated by the cotangent complex, it has actually a graded mixed structure. It has two differentials, one homological given by the DeRam differential and one cohomological coming from the internal differential in the cotangent complex. And you want the closeness to be a condition in the total complex of that double complex, which means that you need to lift your cochain in the cotangent, in the naive second wedge power of the cotangent complex to a cochain in this, to a cocycle in that double complex, total complex of the double complex, and that's the closeness condition. And so symplectic n-shifted symplectic forms are guys that are non-degenerate in this sense and are also closed, equipped with a closing structure in the sense I just said. And once you have this notion of an n-shifted symplectic form, then you can do a lot of geometry with it. So I want to give some examples and then get to the point about the functions. So a comment which may not be obvious if you see this thing for the first time is that the non-degeneracy condition in the definition of a symplectic form, it provides a duality between the tangent complex and the shifted cotangent complex, but it basically says that up to a shift the tangent complex is symmetric, So it actually gives you a duality between the positive degrees in the cotangent complex and the negative degrees in the cotangent complex. And those geometrically are responsible for different aspects of the geometry. The positive degrees are responsible for the Stucky structure on your space, and the negative degrees are responsible for the derived structure, for the modification of the function theory. So that's important to remember, that the moment we allowed those shifts and the moment we started looking at geometries that have these perfect cotangent complexes living in various amplitudes, non-symmetric amplitudes around zero, both stackiness and the derived structure become important, and they actually get intertwined by these symplectic data. Another example or a comment, which is somehow central in this story, is to notice that if you have say a general linear group or a reductive group, then the classifying stack of that group has a canonical two-shifted symplectic form, which is just given by the Killing pairing. It's just that the cotangent complex of the classifying stack is just the dual of the Lie algebra in homological degree 1, and because it's sitting in homological degree 1, the wedge product becomes really a symmetric product shifted by -2, and when you shift by 2, you just get this the quadratic forms on the Lie algebra, and because we are on BG, everything should be G equivariant. This picture is just lifted to the atlas, which is the point. So we are just looking for a G invariant quadratic form, a two-shifted two form on BG is just a G invariant quadratic form on the Lie algebra. Non-degeneracy just says that it's non-degenerate, so that's why you need the group to be reductive. And in this case, you can actually check that there is no closing data. The closing data is contractible or trivial. So it is closed. So the Killing form provides a natural symplectic form on the classifying stack of a group, but it's two-shifted.
Sorry.
Yes.
This shifted setting, where is the alternating?
It is coming because you're dealing with graded algebras. So the alternating condition is a Kuzu grading chance, right? Yeah. So that's why, I mean, because here we have an odd shift, the wedge power becomes a symmetric power. And so that's like somehow the archetype example of a shifted symplectic form in a very simple setting, the classifying stack of a group. And then there is another one, which is a cotangent bundle of a space. So we know a cotangent bundle of a space has, in fact, an exact symplectic form, the logical symplectic form. But if you have a bundle, you can always shift homologically the fiber of that bundle, put it in some homological degree. So if you take the cotangent bundle of a space and put the fiber in homological degree n, so this is just as a derived or a Stucky space, it is corresponding to the spectrum of the symmetric algebra of the tangent bundle shifted by -n. So this guy has also a canonical symplectic structure. It's just the usual symplectic structure on the cotangent bundle, but if you shift the fiber, then the cotangent, the symplectic structure shifts, and it's shifted. So these are somehow the two elementary and basic examples of shifted symplectic forms, and then you use constructions to produce new ones out of them. Okay, so there are two basic constructions which actually secretly turn out to be examples of the same construction, but I'm just going to talk about them separately right now. One says that if you have a shifted symplectic stack, oh, I didn't say this, but ordinary symplectic spaces are just zero shifted symplectic spaces in this definition. So that gives you other examples. So if you have now an n-shifted symplectic stack, you have an orientable space X. So there is some definition of what orientable means. It has to be compact from the point of view of its function theory. And it has to have an orientation class, a fundamental class that maps the cochain algebra of the structure shift to the field shifted by -d. And that has to have like a Poincaré duality behavior on the homology of any shift. And then so we saw that in John Freedom's talk earlier in the week. So if you have one of those guys, then you can look at the moduli of maps from X to F. And it turns out to be a derived geometric stack, which is locally affine representation. And then it carries a natural n-d shifted symplectic structure. So if you have a symplectic structure on the target and you have orientation on the source, the space of maps is symplectic with the shift of the symplectic structure given by the shift on the target minus the dimension of the orientation on the source. And this is some algebraic geometric result. That's an algebraic geometric version of this classical theory, a classical statement in quantum field theory by AKSD. And let me just say that these orientations are not uncommon. They're fairly easy to find. So two standard examples that provide you an all-compact derived stack with orientation of dimension d is just a Calabi-Yau space, compact Calabi-Yau space of complex dimension d, or a compact oriented topological d-dimensional manifold. And there are versions of all of this with boundary, which I'm not going to talk about right now, but they are relevant to the arithmetic context. So that's one way to produce new symplectic structures out of known ones. You start with something symplectic, you look at the maps of something orientable to that symplectic guy, you get a moduli space of maps, which is symplectic with maybe a slightly different shift. And another way is by Lagrangian intersection, which was also mentioned earlier in the week. So if you have a shifted symplectic derived stack, and you have two maps into it which are Lagrangian, and again, in this context, being Lagrangian or being isotropic, it's actually a structure plus a condition rather than just a condition. So having an isotropic structure on a map of derived stacks is a structure. You need to know. So the target has to be symplectic, and then you need to choose a path between the pullback of the symplectic form and zero in the space of closed two forms on the source. So that's the isotropic structure. And then you can ask when it's non-degenerate to make it Lagrangian, and it's the usual condition that the structure induces, it always induces a map from the relative tangent complex of the map to the cotangent complex of the source shifted by one less than the target was shifted, and you want that map to be an isomorphism, which is the Lagrangian condition. And if you have a usual symplectic scheme, smooth Lagrangians are Lagrangians in this sense. But this also gives you a lot of flexibility because it somehow liberates the notion of being Lagrangian from the notion of being symplectic. You can actually build the whole theory by just talking about these types of structures and not mentioning the word symplectic structure at all. yeah, so there is a chicken and egg thing, or what comes first, the notion of symplectic or the notion of Lagrangian. In ordinary symplectic geometry, you cannot define Lagrangian submanifolds without knowing what a symplectic manifold is. But in this geometry, you actually can. So Lagrangian structures on the map from X to a point. The point has only one symplectic structure, which is 0, but you can put it in any homological degree you want. Lagrangian structures on that are just symplectic structures. So these Lagrangian guys are important, and they're also important because they give you another way to construct symplectic structures. So if you have a symplectic derived stack, and you have two Lagrangians in it, then you can look at their derived intersection, their intersection in the world of derived stacks, and that's canonically an n-1 shifted symplectic derived stack. So intersections of Lagrangians in n-shifted symplectic guys give you n-1 symplectic guys. We've seen some of them already mentioned in this example of the Haggard splitting. So if you have a three-manifold oriented three-manifold, you equip it with the Haggard splitting, and you look at the separating surface for the Haggard splitting, then you can look at the derived stack of representations of the fundamental group of that surface in some G. So that by the mapping stack theorem is zero-shifted symplectic because the surface is two-dimensional. And the derived stacks of representations of the two handle bodies mapping to that are actually Lagrangian. And the Lagrangian intersection is the derived stack of representations of the whole three-manifold, the fundamental group of the whole three-manifold. So,
could I ask one?
yes.
I always be confused by that. For that statement, do you need it to be a Haggard splitting?
No, you don't. No, for that statement, you don't. Yeah, this works. I mean, in fact, it's a completely general statement. If you have an orientable manifold, which is a boundary with a compatible orientation, then the derived stack of local systems on the boundary mapping on the bounding thing mapping to the derived stack of local systems on the boundary is Lagrangian.
What does the word canonically mean here?
It canonically means that it depends only on the Lagrangian structures and the symplectic structure. It doesn't depend on any extra choices. All right, so so now let me come to the point of the talk, which is that an interesting case of a Lagrangian intersection is when you are intersecting two Lagrangian sections in the cotangent bundle. And one way to concoct such a pair is to look at the function on a space and take one of the sections to be the zero section of the cotangent bundle and the other section to be the differential of the function, the one form given by the differential function. The intersection of those two, the naive intersection, will be just the critical one of the function. And if you do the derived intersection, this is the derived critical locus. It comes naturally equipped with this DG algebra functions coming by from the derived tensor products of those functions. So this is a Lagrangian intersection of two Lagrangians in the cotangent bundle, the derived critical locus of a function. And in particular, it is -1 shifted symplectic. If the function is just a function, I mean, you can also take shifted functions and then you can get other shifts. So one way to produce a -1 shifted symplectic guy is to take the derived critical locus of a function. And this is exactly the source of this of these functions that potentially can have deep arithmetic meaning. So if in arithmetic topology, if you have something that behaves like a three-manifold, then you can, as I explained, you can understand it as the derived intersections of two Lagrangians in something which is zero-shifted symplectic, the representation variety or stack of a surface, something that behaves like a surface. And so that Lagrangian intersection is -1 shifted symplectic. So when you have something -1 shifted symplectic, you could potentially hope that it's coming from a function. And then that function will have some interesting arithmetic or geometric meaning. And so this is what I want to discuss. So when the question of when this can happen is a question about the good type theorem in this type of derived symplectic geometry. So in classical symplectic geometry, we know what the local structure of any symplectic manifold is near a Lagrangian. So the DeBot theorem says that, say, in the C-infinity or in the analytic setting, or formally in the algebraic setting, any symplectic manifold near a Lagrangian is locally isomorphic to the cotangent bundle of that Lagrangian. That's the symplectic manifold. This doesn't quite work in this shifted symplectic geometry, but almost works. So if you want to say that everything looks like a cotangent bundle, but in this shifted world, as I pointed out, there are actually two natural candidates of what a cotangent bundle can be. One is just the shifted cotangent bundle that I mentioned. Just take the cotangent bundle of a space and put the fiber in some homological degree. But the other is you can take a critical locus of an n+1 shifted function. So if you have a function to the line where the line is put in homological degree n+1, then the critical locus by this Lagrangian intersection picture will be equipped with n-shifted symplectic form. And this also behaves infinitesimally like a cotangent bundle. In fact, the standard shifted cotangent bundle is a special case of this if the function is constant. If the function is constant, you just have the self-intersection of the zero section inside the shifted cotangent bundle, and that's the shifted cotangent bundle itself. So in this derived shifted symplectic world, there is this extra freedom that you could actually modify or deform shifted cotangent bundle into a derived critical locus. And in fact, it's quite easy to check that these two guys are not isomorphic. You cannot make them locally isomorphic. But then a natural candidate for a DeBot statement will be to say that in the derived shifted symplectic world, every near a Lagrangian, every symplectic stack is the critical locus of a shifted function. And that would be the DeBot theorem. Yeah, so I said that these are the local models should be the derived critical loci, and so there is the DeBot theorem, which in its most general form was proven by Ben-Basat, Dubrat, Lucy, and Joyce. And what it says that if you have a derived Artin stack locally affine presentation with an n-shifted symplectic structure, I mean, it has other forms, but I'm going to concentrate on this one. And if the shift is non-positive, then X admits a minimal affine atlas, so that when you pull back the symplectic form to the atlas, you get a derived critical locus for some shifted function on the derived scheme.
Atlas in a smooth topology?
It's atlas in the smooth topology. I mean, it has to be in the smooth topology because of, as I said, minimal, it means it has the minimal possible dimension because you have cohomology, the tangent complex that gives you the stackiness and you cannot avoid it. Mm-hmm. Okay, so this is the theorem. It's a very nice and powerful theorem which gives you that locally everything behaves in the expected fashion. So if you start with something, say -1 shifted symplectic, locally you can write it as a critical locus of a function, and that function will be meaningful. But then when we deal with arithmetic topology questions, especially, you want those functions to be global and you want to be able to evaluate those functions. So it will be useful and it will be important to actually understand what the ambiguity of this local function is. And when can we make them to be global? So that's the question I want to understand. I want to understand how much freedom do we have in moving this local Darboux charts, these local functions, and when can we make them global? Okay, so actually it turns out there is a complete answer to this, that the functions, the realization as a Dirac critical locus symplectically really depend on the existence of foliation, and foliation has to be essentially Lagrangian. So this is the answer, and let me try to make it more precise, and then I'll give you some interesting examples. So here's the theorem that we proved. If you have a Dirac stack, which is locally finite presentation with an n-shifted symplectic form, I want to understand when can this be written globally as a critical locus of a function. Well, one thing that you can notice immediately when you write down a critical locus of a function is that the derived critical locus of a function as a symplectic guy is not just symplectic, but it's also exact. The class of the symplectic form is 0 in the rank homology. So you need to require that if you want to have it, want to have a potential, you need to require that your symplectic form is exact. And so I'll require that. Then the claim is that if you have an isotropic foliation, and I've written the data for foliation, but I haven't told you what codifies foliation, so ignore the words, I mean the symbols. So if you have an isotropic foliation on your derived stack for the symplectic structure, then you can write it as a derived critical locus. In fact, it's even only. So you can find a shifted symplectic structure on something, and that something turns out to be a formal stack that you manufacture out of the foliation. You can quotient your stack by the foliation, you get a formal stack, and then once you know that the class of the symplectic form is 0 and the foliation is isotropic, there is a function on that formal stack quotient, shifted function. You can look at the derived critical locus of that function with its natural and shifted symplectic form. There is a natural map from X to that derived critical locus, which is just induced from the map from X to the quotient. And the claim is that if you pull back the shifted symplectic form on the derived critical locus, you get the original shifted symplectic form. And moreover, if the foliation is not just isotropic but Lagrangian, then this map that we constructed, the map from X to the derived critical locus, is actually a tau. So with
foliation, you think of smooth foliation, you allow singularities.
Well, so in this Dirac geometry word, the word smooth doesn't appear. Yeah, so it actually it does more, right? So singular foliations are certainly examples of that, but there are also foliations that these foliations, they're given essentially by sheaf of L infinity algebras mapping to your tangent complex as a sheaf of L infinity algebras. And the map, there is no notion of the map being injective or anything like that. And so the only condition is there is some local finite presentation condition that says that the corresponding sheaf of L infinity algebras is perfect.
Some local triviality constants.
Yeah.
So for functions, how would you get the foliation?
Yeah, so it's coming.
Your H there is the isotropy structure.
H is the isotropic structure. Yeah. So yeah, I mean, I tend to write foliations as mixed graded algebras. So this is what my L is the generator of the mixed algebra, and alpha and E are the mixed structures. So but you'll see. I'll show you example. But yeah, so this is the statement. The statement is that if you want to have lower potentials up to maybe some metal base change, then you just need a Lagrangian foliation, and it's even only. Okay, so now how can you use that to get interesting examples? So first of all, let me point out that it does connect with the theorem that I mentioned, because for negative shifts, you can check for Hodge theoretic reasons that the class of the symplectic form is always 0. So negative shift symplectic forms are always exact. And zero shifted symplectic forms are locally exact. So the theorem, the conditions in that theorem were consistent with what I'm talking about. And now let me do examples. So in the derived critical locus case, this holds. So if you have a smooth him and a function, you can look at the critical locus of that function, the derived critical locus of that function with its -1 shifted symplectic structure, and the foliation that that you need to take on X in order to reproduce that derived critical locus in that function is you look at the map from X to Z, which is the inclusion, and you take the tangential foliation of that map. There's the relative tangent complex with its liberty.
Sorry, could I interrupt 1 second?
Yes.
I'm backing up a little bit late, but in your previous statement, I thought that in this theorem of
This one?
Joyce, etc., not that one, the Joyce, etc. They weren't they showing the existence of this Darboux function Zariski locally?
Yes.
But then how does this condition of being exact work? Zariski locally, I mean, Durham cohomology then is the algebraic Durham cohomology, right? So why should it be exact?
The Zariski local statement is only in the negatively shifted case.